All right, so we're building our intuition about linear combinations and what vectors do when they're brought together. And in this segment, we're going to go through a number of very important definitions that we're going to be using throughout the course. And the most important one of them really is this notion of a span. We're going to talk about the span of a set of vectors. And really what that means is all of the possible linear combinations you can get from it, which of course is infinite, right? Because if you can take any scalar times each of the vectors before you add them up, then obviously there's infinitely many scalars you could choose. But nevertheless, it's going to be useful to talk about, if I have these two vectors, where can I get to, right? If I take the set of all possible linear combinations, that's showing me all the different points I can get to through some combination of those two vectors, and that's going to be known as the span, all right? So that's a little bit of a foreshadowing. Let me talk about another definition first, and that's the notion of a vector space. Now, this is a pretty heady and ethereal concept in upper mathematics, and we're going to be using it in a very basic way, but for us it just means the world in which our vectors live. And when we say, hey, the vector space we're dealing with right now is the xy plane, we mean it's a world of two dimensions in which there are two-dimensional vectors. Or if we say our world is the three-dimensional space, then it's going to be a world of three dimensions where there's three-dimensional vectors. And of course, we will have many occasions to deal with higher dimensions than that, which we can't, visualize geometrically, but which nevertheless are going to make sense in the computational sense, all right? So that's just what we mean by a vector space. And whenever you hear that in a math lecture or in a math book, it means that although they aren't always quite as tied to numbers as we are, they deal with it in a little bit more of an abstract sense. But that's what it's going to mean for us. And when we say a vector is n-dimensional, it probably goes without saying, but let me just be explicit here. We basically mean it has a length of n, right? So a domino is a two-dimensional thing because you can express it in the xy plane. And a triomino would have three elements, right? So it's basically just how long the vector is. That's how many dimensions it's in, okay? Now, here's the definition that I alluded to in the opening here. The span, and this is really key, the set of all linear combinations of a set of vectors. That is what the span of a set is. The set of all the things you can make from it. So, let's go to the domino game here and consider those yellow dominoes we had and ask what the span of them is. Basically, that's the same as asking, what are all the white dominoes that I can make out of those two yellows? And as we learned, you can make any white domino from them. In other words, the entire xy plane, any point on the Cartesian plane, we can make from those two vectors. On the other hand, the span of those two blue vectors was not the whole xy plane, because as we saw in the last episode, or the last segment rather, you cannot get anywhere except on the line, because those two blue dominoes lie on the same line. The only place you can get is the line that goes through the origin with that slope, right? If you take rise over run, you'll figure out that the line has that slope. It's a little bit steeper than 45 degrees. And so the span reduces to simply that line instead of the whole xy plane. Way, way, way smaller, right? Infinitely smaller than the yellow one spanned. Remember we looked at this set of vectors last time, and I said, hey, are these linearly independent? What do you think? And you might have looked at them and said, yeah, they sure look like it to me, but then I showed that they weren't, because you could actually take the first two and make a linear combination and get the third one. And therefore, since you can get one of the vectors from a linear combination of the other two, that means they're not linearly independent, right? So therefore, this is not linearly independent. Therefore, it doesn't span the entire x, y, z space. There are, in fact, some vectors in three-dimensional space, many, 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 many of them, in fact, infinitely many, that you can't get to. And one thing you might think about is, well, what is the span of that set of vectors then? You've given me three vectors in three-dimensional space, yet you're telling me that they don't span the entire space. Therefore, what is the span of them? And it's a little tricky to look at it and to think of it geometrically, but really what's going on is those three lines that I've given you lie on a plane. There is some plane, it's not straight like this or straight like this. It goes through the origin of the three-dimensional coordinate system, and those three lines are all on that plane, which means no matter how I combine those three vectors, I can't get off that plane to the rest of the three-dimensional space. All right, this is where it starts to get hard to visualize, and eventually you want to abandon your geometric intuition and start just accepting the stuff as it is, because you're not going to have any hope when we get to 50 dimensions, right? But still, it's sort of useful to think about the fact that those blue dominoes dominoes could only get on the line, not the whole plane. And similarly, that deficient set of 3 triominoes that I gave you cannot get to the entire space. It can only get to a plane on that in that space. All right, another key definition here, a basis. What do we mean when we talk about a basis for a vector space? And here's what we mean. 2 things. First of all, it's linearly independent. Second of all, it spans the whole space. So if you've got a vector set and it spans the entire vector space, as our yellow ones did, for instance, and it's linearly independent, as our yellow ones were, then it is a basis for the space. If you have a basis, this is a very important thing. It turns out that every vector in the entire vector space can be expressed in exactly one way using that basis. Okay? And we saw that with the yellow case. For example, if I give you 1, 2, and 4, 4 as my 2 dominoes, that is a basis because those are linearly independent, A, and they span the whole space, B. Therefore, every point on the plane you can form with a linear combination, right? So if you want to get to 6, 8, well, that's 2 of the first one and 1 of the second one. If you want to get to 0, 4, that's 4 of the first one, -1 of the second one. If you want to get to 4, -4, that's -8 of the first one, plus 3 of the second one, etc., etc. And, you know, we established, didn't prove, but I think convinced ourselves that every point you can get that way, and that there's only one way to get each point, right? When I say that to get to 6, 8, you have to take 2 of the first vector and 1 of the second vector, there isn't any other solution that's going to give you 6, 8. That is the one and only one way to get there. And that's true because 1, 2, 4, 4 is a basis. Okay? So if you think about it for a second, there's 2 ways to make something not a basis. One is to subtract a vector from it so that it no longer has enough power to span the space, right? If I said I'm giving you 1, 2, and 4, 4, and then I take away 1, 2, well, now all you have is 4, 4, and that certainly doesn't span the space, right? Because now you can only get on that northeast line. You're basically in the same boat that the 2 blue vectors were, right? So taking away a vector to make it smaller than is required is going to make it not a basis because it doesn't span the space. Similarly, if I add a vector to it so that there's no longer linearly independent, it is no longer a basis either. So imagine if I gave you 1, 2, and 4, 4, and then I threw in 3, 6 also. That is not going to be a basis because adding another element to the mix means that it's not linearly independent anymore. Now you might say, well, can't we still get to the space? I mean, man, we have extra ammo now, right? We have a whole nother vector that we could use in addition to the ones that already span the space. Yes, true. And it does span the space when I give you that third one, but it's not a basis. And it's not a basis because a basis must be linearly independent, and that's because we want it to be the case that every point in the vector space you can get to in just one way. And it's that just one way part that's going to break if I give you more vectors in that set than you need for the basis. There's going to be multiple different ways to get every point because 2 of those vectors can be used to make the other third, therefore there's infinitely different ways to make a point. Okay? So that's what we need to have a basis. Now, there is a special basis called the standard basis, and often we're going to be thinking in terms of that one. And that is sort of the obvious basis where you basically just say, hey, the x direction and the y direction, 1 length each. So in 2 dimensions, it's just the vectors 1, 0, and 0, 1, right? So this guy here basically goes on the x-axis direction, 1 unit long. This guy is unit length in the y direction. Or if we're in 3 dimensions, we've got 1 in the x, 1 in the y, 1 in the z. You can see that these are very, very easy to work with, right? These are obviously bases because clearly neither one of these is a linear combination of the other, right? I mean, one only has x stuff and one only has y stuff. And clearly they span the whole space because if I give you any amount of x-ness and any amount of y-ness, well then obviously you can get anywhere on the plane, and that's true for all these here, right? And in fact, if you think about how you express these things, it's very, very easy. If I say, hey, how do you express 6, 8 in the standard basis now? Well, duh, it's 6 of the first one and 8 of the second. How do you express 0, 4? It's 0 of the first and 4 of the second. How do you express 4, -4? It's 4 of the first and -4 of the second, etc., right? So the coordinates of the vector actually are telling us how much of each of the basis vectors to get because, you know, this is how the standard basis works out. So, just so you know that. This may be obvious. It was to me, but let me just sort of say it explicitly here. If If I've got a vector space, I can find lots of different bases for them, right? We already found 2 for the two-dimensional case. We found 1, 0, 0, 1, which is the standard basis. And we found 1, 2, 4, 4, which was our yellow domino basis. So you can have many different bases, but they all have the same size, right? They all have the same number of vectors in them. That's for 2 reasons. First of all, if you have less than that, well, you can't span the entire space. If I give you just the 1, 2 yellow domino, well, you can't get everywhere. You got to have enough to get everywhere in the vector space. But also, if you have any more than that, you can't be linearly independent, right? If I give you 1, 2, and 4, 4 as your 2 yellow dominoes, there isn't any other yellow domino to have. You can already get anywhere in the plane, therefore any other vector you could get from 1, 2, and 4, 4, therefore it wouldn't be linearly independent, right? And so the last little definition we're going to do here is formally defining dimension. We've been loosely saying, the dimension of a vector, and that's fine, that's what we're going to use as our intuition here. The dimension of a vector space really is how many elements are in a basis for it, which is the same as the definition we had before, right? So if I'm dealing with 3-dimensional vectors, a bunch of vectors that have length 3, that has a vector space of 3 dimensions, right? The x, y, z space. And the dimension of that is 3, and that's because you need 3 vectors to make a basis for it. You can't do it with 2. You can't do it with 4. If you get 4, one of them is going to be a combination of the others. If you try to do it with less, you can't get everywhere, therefore the dimension of that is 3. All right? Let's do some quick review to make sure these concepts are solid. First one, are the dominoes 7, 2, and 1, 8 yellow or blue? Pause the video, figure it out. The answer is they are yellow, and that's because neither one of them can be formed as a multiple of the other, which is all we really need to check in 2 dimensions, right? 7, 2 on a Cartesian plane is clearly pointing in a very eastward-ish direction, whereas 1, 8 is pointing almost due north. They're pointing in different directions, therefore they are not linearly dependent on each other, which gives us yellow dominoes. What about these? 3 blank and 1 blank. Yeah, now those are going to be blue. And the reason is that 3 blank and 1 blank are both pointing in the exact eastward direction, right? If you think of them on a XY plane, they're both pointing due east. Therefore, we are going to, of course, have the situation where a multiple of 1 gives us another one. Clearly, triple the third one gives us the first, for instance. And those are blue dominoes where we're not going to be able to get many places on the plane at all. What's the special name for these dominoes? Those are the standard basis in domino format. Remember, the standard basis basically says for each dimension that I have, let's have a vector that has 1 in each of the directions and 0 everywhere else, and that makes a basis that's really nice to work with. Here's a set of vectors, 5, 4, and 15, 12. Linearly independent or no? No, they clearly point in the same direction. If you take that first one and triple it, you get the second one. Therefore, they are both pointing in an almost straight northeast direction, slightly more east than northeast. What about this one? 3, 0, 0, 0, 6, 0, 0, 0, negative 5. Those are going to be linearly independent. By inspection, you can see that each one of them just has one component, right? This is completely x-ish, this is completely y-ish, this is completely z-ish. Clearly, we can't make any of them from any of the others, therefore they are independent. What about this one? Also a lot of zeros. 3, 0, 0, 0, 4, 0, 0, 2, 0. Alas, no. You can get the second one from the third, right? And that's because, this one's all y, and this one's also all y. So even though I've got 3 of them, and even though each one points only in one direction, we don't have all 3 directions covered. 2 of them have an overlap. How about this one? 4, 1, 0, 1, 7, 0, 9, 9, 0. Can you figure out whether those are linearly independent or not? Those also are not, and I can tell that by inspection just because I'm saying, hey, the third coordinate is 0 for all 3 of these. So that tells me that really we're trying to cram 3 different vectors into a 2-dimensional space, and I can cry foul on that. In fact, I can look at this and say, if I double this first guy and add it to the second guy, I'm going to get the third guy, right? 4 times 2 plus 1 is 9. 1 times 2 plus 7 is 9. Basically, if I'm not even using one of the dimensions, I'm certainly not going to be able to fit 3 linearly independent vectors into the other 2. How about this? Negative 4, 10, 7, and all the rest. Are they linearly independent? That's one where I'm going to bail out and say, you know what, I don't know. That's too hard to say. In fact, we haven't even gone through a general procedure for figuring out whether or not some vectors are linearly independent. We've just been able to figure out a few special cases by inspection, and in fact, in a future episode, we will learn how to do this definitively for all cases. Right now, though, I'm just going to say, there are some cases where you can spot it. Other than that, we just know there's the concept of linear independence. We can't always necessarily verify it for more than 2 dimensions. Here's one where I've taken the same vectors I gave you, and I've added another one. Now can we tell whether they're linearly independent or not? Ah, yes, this one we can tell, and the answer is certainly no. And that's because we only have 4 vectors here, right? And if there's 4 vectors, we only have 3 dimensions, and we're trying to put 4 vectors into them. And there's clearly not going to be 4 different linearly independent directions in a 3-dimensional space. That's just impossible. So remember, we've sort of maxed out the space once we have 3. There's absolutely no way to fit 4 different linearly independent ones in there. All right? Good job on this. Stay tuned, and we will talk about some Python and R applications in the next segment.